Hello y'all, we are Memphis University and we are back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today is going to be a big one, folks. Today we are going to be talking about U-substitutions. So U-substitutions is going to be one of our main ways to take integrals both on the AB exam, the BC exam, college calculus exams, all across the world. So if you remember fondly back on our derivative days, remember that and when we were learning derivatives, we were struggling a little bit, especially with one rule, but we ended up loving that rule, hopefully, because that rule became the most important rule. That rule, of course, is the chain rule. And we used the chain rule maybe thousands and thousands and thousands of times as we were walking along our calculus journey. And today we're going to be learning the reverse of chain rule, the equivalent of chain rule for integrals, and that's going to be U-substitutions. So just that, like chain rule was involved with composition of functions when you had a function within a function, U-substitutions will also be functions within functions for antiderivatives. But just like with chain rule, it's going to be a bit of a process to learn. It's certainly harder than just taking integrals with power rule, this U-substitution process. So what our goal is today is we're going to try to list out the steps first. Then we're going to focus on certain some of the steps because some of the steps are quite difficult. And then once we do that, let's just do example after example after example after example until we're more comfortable with these questions. So let's get started. This is going to be a fun little video. It's going to be by little, I mean very long video, but hopefully you can enjoy the ride. Let's learn U-substitutions. Keep in mind that we're going to be doing indefinite U-substitutions, meaning that we're not going to have numbers on our integrals. That'll be for our next video. And remember that the point of U-substitutions, and really the point of any integration method, is to change a harder integral into an easier integral. And so that's what we're going to do. We're going to change this integral that involves a lot of x's and a lot of inside functions. And using a U-substitution, we're going to change that x integral into a u integral and make it easier. And let's just see how that works. So again, we're going to be talking about indefinite U-subs today. Indefinite U-substitutions. So let's write that down. So the first step is going to be finding the inside function that I've been alluding to. There's always going to be an inside function. That's going to be our u. So we're going to find and choose u. So find and choose u. We're going to focus on this step because I think that this is oftentimes the hardest step. Sometimes it's the easiest step, but it is going to be a step that we're going to mess up because there's not one way to do it every single time. So I'm going to talk about this step in particular after we talk about all the other steps. But keep in mind that u is going to be some function of x, so we can just call it f of x. The second step is the easiest step, but just be wary that we're going to be taking derivatives in this process, even if we're doing integrals, because it will take a derivative and then we'll slowly do an antiderivative. So just don't confuse derivatives and antiderivatives as you're doing this process. But the second step is going to be always this step right here. It's going to be du. We're going to take a derivative, so it'll be du over dx, but we're going to always bring the dx over, and I think everybody in the world does that. So it's going to be f prime of x. We're going to take the derivative, and we're going to times the dx. So again, this dx is usually on this side, but we're just bringing it over, as you'll see. The third step is probably the step that you can improve the most as you're practicing these. A lot of my students are going to struggle with this third step. It's going to be changing all the x's to u's, but as you practice this, hopefully this will make more sense. So what we're going to do is we're going to sub in, that's why it's called U-substitutions, sub in, if I can spell the word sub, it's not very difficult, sub in all the x's, sub in all the u's into x's, I think would be the particular, the actual way to say this, sub all the u's into x's. Using steps 1 and 2. Using 1 and 2. So again, we're changing all of our x's to u's. We don't like the variable x because it's too complicated. We're going to go to our variable u using these first two steps. And we're not greedy folks, so we're not going to do everything all at once. We're not going to be like, oh, let's change all the x's with u's. What I recommend is to do this one line at a time. Do one line at a time. Meaning that we'll use step 1 first, change some of the x's to u's, and then we'll do step 2, change the remaining x's to u's. We sub in one line at a time, replace some of them and replace some of them. And again, we'll see this in action. So by step 4, it's actually going to be one of the easier steps because it's the step that we're used to. Now, step 4 is going to be take the antiderivative. So take the antiderivative. By step 4, you need to have only u's. So take antiderivative. And it will be u's, and it will be an easy antiderivative. Hope you'll know that you have done it right because you'll be able to take this antiderivative. And finally, after you take the antiderivative, just replace the, I don't know how to spell the word replace either, just replace the u's back with x's. So that's all what it's going to be. So again, steps, find a u. It's going to be a difficult step, but we're going to find it. Then we're going to take the derivative. Then we're going to try to change all of our x's to u's. This is going to be the key steps, step 1 and step 3. And then hopefully by that time, we'll be able to take the antiderivative with respect to u. And then we're going to replace our u's with x's in our answer. And that's going to be it. Again, this process might mean very little to you right now. But hopefully as we do examples, you'll see like, oh, it's the same thing over and over and over again. There are variations in each step. But as we do more and more questions, we'll be able to be more comfortable as we can say, we've encountered so many questions, we should be good to go. But before I do start doing examples, I do want to talk about step 1, how to find the u and give you hints on how to find the u. And I'm going to be alluding to those hints throughout the video. So let's focus on step 1, how to choose a u. And sometimes choosing the u is the easiest step sort of given. But sometimes it's the most difficult step. It's the step that you're going to mess up, and then when you mess up, it's just going to be really, really bad. So let's talk about this, how to choose the u. And just keep in mind that in life, sometimes we run into problems, sometimes we make mistakes. You're going to choose the wrong u some of the time, and that's going to be okay. It's nice to recognize when a question goes awry. So if you do choose the wrong u, basically what happens is you'll just get stuck very easily. No need to cry, no need to quit, no need to rip up the paper. All you need to do is just erase your work and just try a different u. But how do you choose the u in the first place the right way? Well, in the easy questions, you're finding the inside function. Because remember, again, u subs is the opposite of the chain rule. It deals with composition of functions. So what you're going to do is you're going to choose a function that's inside another function. So usually you choose an f of x that's wrapped around something else. So choose an f of x that's in parentheses. So maybe f of x will be in parentheses. Maybe f of x will be in a square root. Maybe f of x will be in an exponent. And then maybe f of x will be in a denominator. So these are all good things to choose because we were choosing inside functions. But sometimes it's a little bit trickier because sometimes you have multiple things in parentheses, or sometimes it's not as obvious as what is the inside function. So what I say is choose a function whose derivative is also in the question up to a constant. So this is the sentence that I'm going to be talking about a lot. We're choosing an f of x where f prime of x, meaning the derivative of f of x, is in the question as well. So in the question as well, up to a constant. So what do I mean by this up to a constant phrase? This is the phrase that sort of gives students the most trouble. So what do I mean by up to a constant? Well, you'll see that there's going to be questions where there's going to be x to the 5th in the question and x to the 4th in the question. And what I argue is that x to the 5th will be a good choice for u. If you take the derivative of x to the 5th, that's going to be 5x to the 4th, of course, using the power rule. And while that's not exactly x to the 4th, it's going to be very, very similar to x to the 4th. So basically, we're choosing functions whose derivatives, while it might not be exactly there, it matches on the x's. I don't really care about the constants because I'll deal with the constants later. So for example, if I see the function cotangent x and also in the question is cosecant squared x, while the derivative of cotangent x is not exactly cosecant squared, it's negative cosecant squared, cotangent x will still be a good candidate for you because its derivative, while not exactly in the question, is basically in the question. The x's match and it's only differing by a constant, so that's what I mean. And we'll talk about this later. We'll see like, oh, this function's derivative is right here, except if you multiply it by 3, for example. But we're going to still choose that function there, as we'll see in these examples. And the third thing is you just try something and you need to be able to sort of predict a few steps here and there, and then you'll be like, oh, I can take the antiderivative of what's remaining, so that's going to be a u. So choose a function where after you do the u-step process, you need to be able to do the antiderivative, where you can take the antiderivative. The antiderivative of whatever is remaining. Not of fx, because that's going to be taking the derivative, but whatever is remaining. Again, this might make little sense. We're going to be really focusing on 2 for our harder questions. So let's just start with examples. Let's get going, friends. It's time. We shouldn't delay it any bit longer. Let's erase this and let's go for our first example. How exciting. What a wonderful morning. So again, we're going to do the integral of, let's do our example that we talked about earlier. Let's do cosine. Cosine x to the 5th times dx. So this is going to be our first example. How exciting. So just keep in mind that just like with derivatives, you can't just take integrals of products, just take the antiderivative of this, take the antiderivative of this. I wouldn't even know just the antiderivative of this. So this is the u-sub process. Again, what we're going to do is we're going to try to change our u, and we're going to focus on this step because there's a lot of functions here, so there's a lot of things that can be u. There can be x to the 5th, there can be cosine x to the 5th, and there can be x to the 4th. So that's 3 candidates for u. But what I argue is that u should be just x to the 5th. And why is that so? Well, there's 2 reasons. First off, it's inside another function. It's within parentheses, so that's why it's a good choice. Another reason why is that its derivative is right here. It's not exactly there, but it's basically there. The derivative of x to the 5th is 5x to the 4th, while this is just x to the 4th. That's good enough for me. So this was our first step, choosing our u. The second step is the same every single time. What you do is you take a derivative. Keep in mind that the derivative is du over dx equals 5x to the 4th using the power rule. Again, in the second step, you are taking a derivative, unfortunately, in an antiderivative question. But what everybody does is we're treating this as a fraction finally, and we're going to bring this to the other side. Du over dx, numerator, denominator. I don't want this fraction, so we're going to change it du to be in terms of this. So again, usually people skip to this step. When they have their u, they'll write du on one side, then they'll take the derivative, and then they'll write times dx. So this third step, because we did the first 2 steps, choosing the u, writing this step, which was the easy step, what we're going to do is we're going to change all of these sort of dastardly x's into u's. And again, what I recommend is try to do this in 2 times. Don't go too greedy. Don't go just shoving in all these x's. Let's take our time. Let's enjoy the moment. So what we're going to do is we see an x to the 5th. We chose u to be x to the 5th so that we get cosine of u right here. So this is going to be my guy. Again, I'm replacing this x first line with u. Then what I'm going to do is I'm going to look at the remaining x's, and hopefully, if I'm doing this correctly, it should be in this line right here. So notice that what I have left, I have cosine of u. What I have left is this guy right here and this guy right here. X to the 4th times dx. These are the remaining x's, and it's okay. We're including dx as well because it has an x in it. But notice that I am doing this correctly because x to the 4th dx I can find in my line right here, my second line. So this is substituting in the second thing. So I have x to the 4th dx, and what I'm going to do is I'm going to isolate x to the 4th dx so I can replace x to the 4th dx with some u's. But notice that I have 5x to the 4th dx. I just want x to the 4th dx. So what I'm going to do is I'm going to take the 5 and bring it to the other side. So that's going to be x to the 4th times dx is equal to du over 5. I like to do this step. Some students do not like to do this step, but I like to do this step. So again, we're changing all of our x's to u's. We first changed this cosine x to the 5th to u, so that's this step right here. And we had x to the 4th dx, which is what we isolated. So we're going to, instead of writing x to the 4th dx, we're only going to write du over 5. So it's going to be cosine u du over 5. And Always in these questions, you're going to have some sort of constant, maybe 1, maybe 2, maybe divided by a fraction. So when I have this constant, just like normal, I like to not put it inside the integrand. I like to take it out. So that's why I'm going to have 1/5 here. So this is, again, the step 3, which is the most difficult step as you're doing this in the beginning. So I'm going to repeat myself. Again, you replace all of your x's with u's, 2 steps. So first I replaced this x to the 5th with cosine u. Then I saw that I have x to the 4th and dx left. So what I did is I isolated that guy and I subbed in, that's why it's called U-Substitutions. I subbed in x to the 4th and dx with du over 5, but I always like to take out my constant and one little step here. And notice that I'm doing this correctly because there's no x's left. I changed all my x's to u's, and that was the point of U-subs. So now what I'm going to do is I'm just going to take this antiderivative. At this step, you should be able to take the antiderivative. It should be either what I call a table integral, literally just a memorized integral, cosine, secant squared, 1 over 1 plus x squared, e to the x, all those, or just doing the power or something like that. So the integral of cosine u, we have a 1/5, so it's going to be 1/5, and the integral of cosine is going to be sine, because the derivative of sine is cosine. Don't forget your plus c, because we are doing indefinite integrals. And then finally, the very last step, the easiest step, replace your u with x to the 5th. So it's going to be 1/5 sine of x to the 5th, and we are done. One little thing is that if you want to check your work, if you're one of the students that like to see if they did it right, you can take the derivative of this and see if you got this. So what's the derivative of sine x to the 5th? That's going to be cosine x to the 5th times 5x to the 4th using the chain rule, and the 5 and the 5 would cancel, and we would be left with this. So again, anytime you have an integral, you could try to check yourself to see if you have the correct answer, because it's nice to have the correct answer every once in a while. But again, steps. Choose a u. U is equal to x to the 5th. Take the derivative immediately, 5x to the 4th times dx. Then you replace all the x's with u's. So I replaced this x to the 5th first, so it's cosine u. Then I saw that I needed x to the 4th dx, isolated that. It ended up being du over 5. It has to be in this second line if you're doing it correctly. I took out the 1/5, took the antiderivative, and then replaced it with u. And that's all it is. It is a very long process, but as you get your sort of bearing down, as you keep practicing this, you should be more comfortable as you get going. So let's not delay it anymore again. Let's not lollygag. Let's do another example. So I'm going to erase this. Erase this, erase this, erase this. So integral of, let's have x cubed plus 3x. Then I'm going to multiply this by x squared plus 1. I think that's what I want. I'm going to raise this to the 6, and I'm writing dx. So let's put the integral closer to the question. That should work. I think it does. So we've learned in some of our basic integrals that sometimes you want to expand in order to do integrals, but notice that there's no way I'm going to expand this because I have to raise it to the 6. So it's a u sub time. So it's going to be u is equal to something. But it's a little bit harder than our first hint question because there's 2 questions as we choose this u. There's 2 things that are going to be in parentheses. So there's really a lot of choices that I can let my u be. Should I let my u be all of this stuff? Should I let my u be this? Should I let my u to be this to the 6? So what I say is, again, choose something whose derivative is sort of in the question. So what I'm going to do is you choose the more complicated one. I'm going to choose x cubed plus 3x. And why is that so? Well, its derivative, while not exactly this, is this times a constant. So what's the derivative of this in your head? That's going to be 3x squared plus 3. That is really similar to this. So that's why this is going to be a good choice for you. So again, you choose functions whose derivatives are sort of in the question. Then we are going to do the du step. This is the easiest step because it is the derivative step. Just take the derivative of this, 3x squared plus 3, and then multiply by dx. So now we are ready for the subbing in step, changing all of our annoying x's to u's to make it a little bit easier. So again, I like to do this in 2 steps. Within this one single changing all the x's to u's. What I do is I look at why I chose this u and replace all those x's first. So notice that x cubed plus 3x goes right here. So that's why it's going to be u to the 6. U to the 6. Then I look at what I have x's remaining. looks like I have an x squared plus 1 in dx. I need to sub in all of these. I need to replace all of these x's with u's. So I'm going to look for it. It has to be in the second line if I'm doing this correctly. And notice that it is basically in the second line. Right here I have 3x squared plus 3 times dx. I want to sub in x squared plus 1 times dx. So what should I do? I need to divide by 3 and I should be good to go. I like to write out this step, x squared plus 1 times dx. What is that equal to? Again, I'm dividing by 3 du over 3. So what I'm going to be able to do is I'm going to be able to replace all of these x's with du over 3. So that's what I'm going to do, du over 3. But I like to take out the constant, so it would be 1/3. So again, all of these x's I want to replace. I replace some of them with u's, u to the 6th. Then I see which ones I have remaining. They should be in the second step if I did the second step correctly. So what you want to do is isolate that thing. In this case, it's x squared plus 1 dx equals d over 3. And then just replace all of our dx's instead of writing all this stuff. This double over here, sorry, I already underlined it. Instead of writing this, we're just writing d over 3, but we're taking out the constant. And now for an easy step, just the power rule, add 1 and flip the new exponent. So it looks like it's going to be u to the 7th because it's 6 plus 1, that's 7. Then you divide by your new exponent, so it's going to be 1/3. Because there was already a 1/3 times 1/7. This is the flip the new exponent. So this is going to be 1 over 21. And then remember that you do want to replace your u because you want your answer to be in terms of x's. X cubed plus 3x. And then it's to the 7th. And then don't forget your plus c. And that's how you do u subs. Again, you choose a u. You take the derivative. You start replacing all your x's with u's one line at a time. First, shove in this guy into your u. Then look at how many x's you have left. Isolate that in the second line. So alternate that second line so that exactly what x's you have left. And it will be there, I promise. And then once you have that, what you're going to do is a nice little substitution of those remaining x's. Take out the constant, find the antiderivative, and then replace the u with x. And that's what it is. It is, again, a very long process and a process that requires a lot of steps. So that's why practice makes perfect. Let's keep going. So I'm going to erase this now. So just like with derivatives, keep in mind that in chain rule, usually once you get chain rule down, you get the more obvious chain rule questions where it's like, oh, there's definitely an inside function like sine of x cubed or cosine of e to the x or something like that. There's definitely an inside function. What students start messing up is sort of the small chain rule questions where you don't think that there's an inside function, like sine of 3x or sine of negative x, secant of negative x, something like this. And it's the same thing with U-substitutions. So for U-substitutions, even if it's a small inside function, if it has a derivative, you need to incorporate it with U-substitutions. So let's see that in the next two examples. So my next one is going to be 8 over 5x plus 1 and right times dx. So let's get going with the process. Not many things to choose for you. One thing is that you'll practice, you'll see as you're doing this practice is that when you have fractions, a lot of times the denominator of the fraction is a good choice for you, especially if it's just to the 1. If this were 5x plus 1 squared, I would probably just still let u be 5x plus 1 because that would be within parentheses. And keep in mind that if it was 5x plus 1 squared, you wouldn't want to choose the entire denominator. One thing is that your derivatives should get simpler, so you shouldn't be using too much chain rule as you choose your u. So let's write u is equal to 5x plus 1. Again, nice little guy here. When you take your derivative in the second step, it shouldn't get more complicated, it should get simpler. So that's another way to help you choose your u. So this second step, again, is pretty easy. All you do is you take the derivative of 5x plus 1, that's just going to be 5, and then remember to multiply by dx. So now all we have to do is replace all of our x's with u's. So why did we choose this u in the first place? It's so that we can get u on the bottom here. So it's integral of 8 over u times d, okay, sorry. Sometimes people write times dx, but let's not write that. So again, I take my u, replace it where it's supposed to go, and then I look at the remaining x's. Dx counts as an x, so it looks like my only remaining x is this dx here. So how I'm going to do this? Well, again, dx will be in this line, and I just need to isolate just the dx, so it's going to be dx over du divided by 5. So instead of writing dx, I'm going to replace it with du over 5, so that's going to be du over 5, but I'm not going to write over 5, I'm going to always take out the constant 1/5. If you want to, you can even take this constant out, because taking out constants of integrals is just a nice little habit so that the integrals become easier. So we're going to take out that constant as well, and notice that we have achieved our goal. All of our x's became u's. This 5x plus 1 became this u, and this dx became du. Now I'm ready for the integral. What's the antiderivative of 1 over u? Keep in mind that it's not the power rule. We don't want to write it as u to the negative 1, because this is ln. So it's going to be 8 over 5 ln of u, technically the absolute value of u, and then what we're going to do is we're going to replace this u with 5x plus 1, 8 over 5 ln of 5x plus 1, and we are going to be done. So again, same process, choose a u, take the derivative, then replace some of the x's with this u, look for the remaining x's that you have left, in this case dx, isolate that thing, replace that thing with the remaining dx's, so that was the point, or the remaining x's, and then by this step, take out all your constants, and you should be able to take the antiderivative, and then once you take the antiderivative, just replace your u with x, and you're good to go. Let's see the example that I alluded to earlier, where we don't change this question too much, so you don't have to do too much more work. But let's see what happens if it's 5x plus 1 squared instead. So 5x plus 1 squared. So the same thing. Again, you're going to be choosing the wrong u as you start this process. Let me just show you what happens if you do choose the wrong u. If you have the u, this is going to be wrong, but let's say we want it to be the entire denominator, because sometimes they use the entire denominator, like the previous one. So let's say I did this. Well, what's the second line would be? The second line would be 2 times 5x plus 1 times 5, because that's the chain rule, times dx. And notice that it's probably wrong, because as we start replacing our u's, we would have 8 over u. So the only x that I would have left is this dx, but I introduced, when I was doing this question wrong, this x right here. So this is why this is probably wrong. I introduced an x and I won't be able to replace the dx with all of this. Remember that if you're doing this correctly, the second line will be whatever x's you have left remaining times perhaps a constant. So this is going to be wrong. Let's do it correctly. Again, if you do a u sub wrong, it's going to be okay. It's going to be okay. Nobody's going to judge you. Perhaps only your teacher or maybe yourself. All you do is you just get stuck, erase the question, try to choose a new u. So I argue that u is just going to be 5x plus 1 because its derivative is basically just dx times a constant. So let's see how this works. Again, du is just going to be 5 times du. And now we're going to change this harder integral to be a u integral. So we're going to take this 5x plus 1, put it in where it's supposed to go. It's going to be 8 over u squared. And then I need to find the remaining x's, but this is correct as opposed to our previous wrong thing, because notice, if I write this correctly, this should be dx. Notice that what I have left, the only x that I have left is just right here, dx. I didn't introduce any extraneous x's, so all I have to do is isolate again. So it'll be du over 5. And then I'm going to take this dx and replace it with du over 5, so it's going to be du over 5, but again, I always like to take out my constants, 1/5. This is the power rule, so just be careful that not every single denominator you have is going to be ln. ln is only for things that are like 1 over x or 1 over 3x plus 1 or 2x plus 1, 1 over a line basically. This is a quadratic, so it's going to be the power rule. So I'm going to rewrite this as 8 over 5 because I took out an 8 as well. Integral of u to the minus 2 times du. Now I'm going to do this lovely integral right here. How do you do the integral of u to the minus 2? Well, again, it's the power rule, so you add 1, u to the minus 1, then you flip that bad boy, so it's going to be 1 over negative 1, so this constant is going to be negative 8 over 5 plus c, and then finally, let's replace the u at the end. We can change it back to a fractions if that sort of fits your sort of liking. It's going to be 5, and then what's the u? It's going to be 5x plus 1, and then it's going to be plus c. So again, You're going to mess up choosing the U's, but just be careful. Sometimes the best thing to do is just get used to messing up over and over and over again so that you know when you mess up, when you sort of get stuck, and then when you know when you're messed up, then it's just easier to just start over again. So let's do a few more examples. I'm trying to really emphasize on the small U-subs because those are the ones that appear quite often on AP exams and college calculus exams because they're theoretically easy, but people don't notice them as U-subs. People just start taking the antiderivative. So this is the integral that I do quite often, the integral of 1 over e to the x dx. This is not ln as well, even if it's a fraction. Remember, ln is only 1 over x or 1 over 5x plus 1 or something like that. This one, you do have to do a little bit of algebra. You need to write this as e to the minus x, which is what I'm going to do there. And then now we're going to try to take this integral of e to the minus x. Keep in mind that this is technically a U-sub and people get confused. But the only integral that I memorized is e to the x, or sine of x, or cosine of x, secant squared of x. As long as you put an inside function there, it becomes a U-sub, just like with chain rule. You don't chain rule e to the x, or you don't chain rule sine of x, cosine of x, tan of x, 5 to the x, but you start chain ruling things like cosine of x squared, or tangent of secant x, or e to the ln of 5x, or even sine of negative x, cosine of 2x. As long as I'm changing that inside function and the inside function now has a derivative that's not just 1, you have to U-sub. So let's U-sub this pretty easy example. What we're going to do is we're going to choose this as my u because this is an inside function. It's going to be u is equal to minus x. The other possibility that you might have is that u is this entire thing, but that won't make any sense because then its derivative would be e to the minus x times negative 1, and you would have 2 e to the minus x as the sub in, and it would just get really awful really fast. In this case, when we choose this correct u, our derivative is of course going to be just negative 1 times dx. So now we can start replacing all this x integrals with u's. So it's going to be the integral. I chose this u for a purpose so that I could put it on the top here. So it's going to be e to the u. Then I'm going to look for my remaining x's. Looks like I have a dx here, so I just need to solve for this. What is dx going to be? Well, dx is going to be just du over negative 1, which is the same thing as negative du. So it's going to be du. I'm replacing this dx with this du line, putting a negative in front. Then now I hit the question that I like, hit the easier question. I change all my x's to u's. So what's the antiderivative of e to the u? This one I can't take without a u-sub because it is literally just e to the u, e to just the single variable, no negative attached to the guy. So now I can just take the antiderivative. The antiderivative of e to the u is of course e to the u. So it's going to be minus e to the u. Finally, we're going to replace our u with this, the easiest step, e to the negative x plus, and that's all it is. So again, just be careful of those little u-subs, just like we wanted to be careful of little chain rules. So I'm going to erase this guy right here. Let's do a few harder examples because you will encounter these in the wild as you're doing these questions. So let's maybe do 3 more that I know off the top of my head. So the first one I'm going to do is the integral of sine to the 7th x times cosine x times dx. So again, when you encounter this question, you see that this is potentially a u-sub, especially on the AP exam where almost every integral is a u-sub. But there are candidates for u-subs, candidates for these u's. Looks like I have 3 candidates: sine of x, cosine of x, or sine of x to the 7th. One of them I think I can easily eliminate it as a candidate because if I chose all of this sine to the 7th x, well, that derivative is very complicated. It's 7 sine of x to the 6th times cosine of x. So it doesn't seem like I'm doing anything right because remember that the derivative is usually simpler and it'll be very easy to replace things. So there is an argument of whether we should choose sine of x as our u or cosine of x as our u. And we can't do our rule of what's the derivative of the other because one is the derivative of the other and this one is the derivative of this, besides maybe a constant of negative 1. So that's not a good choice. But we can use our fact that we should choose functions that are inside other functions. Cosine of x is just on the outside here, just minding its own business. But sine of x is involved in to the 7th. So that's our good choice for u. So it's going to be sine of x. Then we start doing the process. We immediately take the derivative. You don't even have to look at this. You just take the derivative, cosine x times dx. This derivative does look very nice on this Saturday morning because notice that it looks exactly like this. So now what we're going to do is we're going to replace our x's with u's. So it's going to be integral. Well, sine of x, we chose this as our u so that we would get u to the 7th. And then we sort of try to find all of our remaining x's. And lo and behold, it's exactly right here. How crazy. We don't even need to bring over a constant. It's exactly this. So all we're going to do is instead of write this, we don't want to write x's. We're going to write this times du instead. So now, time for the integral. Notice that we have hit an easier integral. There's no x's. You cannot have x's when you do the u integral. It has to be all u's. You have to change all the x's into u's using these two lines. So what we're going to do is we're going to take the antiderivative. It's the power rule. We're going to add 1 and then flip the new exponent. So it's going to be u to the 8 over 8. So 7 plus 1. You can write this as 1/8 times u to the 8th, of course, plus c. Very last step, replace the sine of x with that. There's going to be sine of x to the 8th over 8. I'm going to squeeze in a little 8 here, plus c. So as you do these questions more and more, you'll get better at this process. You'll get better at choosing the u's. You'll get better at replacing the x's. But there are some that are a little bit harder. So let's do 2 more. Some that I really only know how to do because I've done these for a long time and sort of know what to go for. Let's do the integral of secant squared root x times dx. So another hard question, definitely a u-sub. So the use that people sort of can recognize is that the u will probably be square root of x. And why is that? Well, a, it's inside another function, so that's a good sort of sign. And then what's the derivative of square root of x? Well, that's 1/2 x to the negative 1/2. And that's also in the question, but it's written as a fraction here because x to the negative 1/2 can be written as 1 over square root of x. So one thing I would suggest in this question, which is going to be very similar to other ones that you might see, it might be e to the square root of x over square root of x, or it might be sine of square root of x over square root of x, or cosine of square root of x over square root of x, or something like sine of 1 over x cubed divided by x to the 4th. Very similar thing. What you want to do is you want to write this denominator as a negative exponent because it'll be easier to sub in my opinion. But again, I only know this because I've done these questions a lot of times. So it's going to be the integral of secant squared of root x. And again, the best thing to do is write this as x to the negative 1/2 times dx. Just a nice little step and it'll make our substituting lives a little bit easier. So let's do our u. So again, we chose square root of x because its derivative is in the question, times a constant. Also, it's inside another function. So it's going to be square root of x. Du, as we mentioned before, if you want, you can write this x to the 1/2. Definitely no shame in that. Keep in mind that we're doing the derivative power rule instead. So we're taking this power, dragging it to the front. 1/2 x to the negative 1/2. Or I can write negative 1/2 times dx. So now let's just start changing all these x's into u's. So it's going to be the integral. I chose this as my u so that I can replace it inside the secant squared. So it's going to be secant squared of u. Then I see what x's I have remaining. If you want, you can certainly underline them. And if you're doing the question right, it should be in the second line. It might not be the exact thing as the second line, but it should be in the second line. And it is. Notice that it's exactly this. I need to replace all these x's. They're right here. I have found them. So what we want to do is you want to isolate this. So there's going to be a constant. What we should do is bring the constant to the other side. If we bring the 2 over, it's going to be 2 times du. And then again, you're doing this to change all the x's to u's. We found them, we isolated them. So let's, instead of writing this little weirdness, we're just going to write 2 dx and t du instead, not dx, du. So it's going to be 2 du, but I always like to take out my constant, so I'm going to write 2 in the front here. And now notice that no more x's, so that's a good sign. Also, I need to be able to take the antiderivative, but I do know the antiderivative. It's just going to be tangent. This is going to be tangent of u plus c. There's a 2 in the front, and at the very end, replace the u with what it is. 2 tan of square root of x plus c. And that's it. So as you do these questions more and more, you'll be able to recognize these simpler tricks. being, oh, I need to write this as this. If you didn't write it like this, you could potentially do the question, but some people will get confused with the square root of x, because as they do the U-sub, they want to replace this with u, and then the question becomes a little bit weirder, and you can't do that. So again, as you do these questions, you should be able to recognize, oh, it would be easier to write this as x to the negative 1/5, half, because when I take the derivative, it will look like that. But again, these questions get very, very difficult, so let's try to do a harder one. Let's try to see where it's just very, very difficult in order to sort of solve these questions, and just practice is the only way where we'll be successful. So my last one of the video is going to be this, the integral of e to the x over 1 plus e to the x squared times dx. So why is this tricky? It's because there's so many choices for you. There's e to the x itself, there's e to the x squared, there's 1 plus e to the x squared, there's all of this stuff. So again, what we want to do is use our hints in order to try to choose this u. So I'm going to argue that u is e to the x. And why is that so? Well, A, it's in parentheses, it's getting raised to a power. The second thing is that its derivative is also in the question. It's just right here, e to the x times dx. And then finally, if I replace all of this stuff and sort of cover it up, I'll notice that I'll have 1 plus u squared, and I know the antiderivative of that. So that's going to be my u, e to the x. Once you choose a u, everything is forced. You choose the du, you just start subbing in. So this line, no matter what the question will be, if I chose this as my u, my next line would be e to the x times dx. That's great because it's right here. Let's go to change this into a u integral. So I chose this as my u so that I could replace it right here. This is where it gets a little bit tricky. Some people might be tempted to plug in u as well for right here, but I need to leave one of the x's, one of the e to the x's for du. So I'm only going to replace this with 1 plus u squared. And again, it's only because I have a good sense of this, why I'm not replacing this u with ex, because I'm like, oh, I need to leave one of them for the du. And we're exactly at that point now. Once I replace the u with e to the x, you'll see that I have e to the x times dx. That's exactly this line. So instead of writing e to the x dx, instead I can write just times du. I change my x integrals into a u integral by replacing all these u's, leaving 1 e to the x for u, 1 e to the x for du. And again, I know this antiderivative, it's inverse tan to the negative 1 of u plus c. Replace the inverse tan u with e to the x. Inverse tan of e to the x, and that's our last question. So U-subs, sort of a process that people really struggle with at the beginning. Choosing our u's, changing on the x's with u's is also a difficult step in my opinion. It's definitely no shame in struggling with this at the beginning, but hopefully we will progress as we practice more and more examples. Just remember, you choose a u, you take the derivative, you start subbing in all your x's to u's one line at a time. So you chose that u for a purpose, replace that. Look at what all your dx's and x's that you have left. That should be in the second line. You should be able to isolate it by maybe bringing a constant to the other side. Then you change your x's and dx's to that du, and hopefully by then you'll have an integral that you'll know. You'll take that antiderivative with respect to u, and then finally replace the u's with x's in the antiderivative. But this is a process that does require practice. Just like normal, we do have another video, our Girls Teach Calculus video, where one of my former students practices several of these examples. She goes over slowly how to do the U-step process, and then she practices them. She focuses on choosing u's, she focuses on changing x's to u's. So be on the lookout for that. I'll put that in the description below again, and it's probably better in a video than this one. The explanations are a little bit cleaner. But if this was useful for you, we would appreciate it if you like and subscribe to our channel. And for our next video, what we're going to be doing is this same thing, but instead of indefinite U-subs, we're going to do definite U-substitutions. So we're going to add numbers on top of the and bottom of the integral, and we'll see that it's a very similar process. So if you get this, you'll probably get that one. Hopefully I will see you then. Thanks again for watching, and I hope to see you next time.